Hello friends, welcome to my channel. Now in this session let's see antenna pattern characteristics. So the radiation pattern of an antenna is a plot of magnitude of the far zone field strength versus position around an antenna. So basically what he's saying, radiation pattern can be plot with basically using a magnitude of far zone field strength, okay, and also versus the position around the antenna at a fixed distance from the antenna. Thus the radiation pattern can be plotted from the pattern function. Pattern functions are what? F theta and f phi, right, versus their angle. So angle of plane pattern and an angle of azimuthal plane pattern. So basically for an what is elevation plane pattern and azimuthal plane pattern, we'll see. So elevation plane pattern is the equivalent to the pattern when we cut the 3D radiation pattern vertically, okay, and vertically if you cut, how it will look. And azimuth pattern is equivalent to the pattern that when we cut the 3D plane pattern horizontally, okay. So basically how it was uh, elevation pattern is cut vertically. I have cut this, and horizontal I am cutting like this, okay. For suppose let's have a donut, okay. For example, let us have a donut. So this donut will be like this, right, okay, or a torus, I think it's so you understand it how it will be. So when it comes so let us actually I am seeing the top view. That means basically it will be looking like somewhat or example, let us take this only. For simply we'll take a cylinder, okay. We are taking a cylinder. Now if I cut, what is the elevation pattern when we cut this 3D rotation pattern vertically? For example, this is the this is how the radiation pattern is looking like. Now I am cutting this in vertical. So when I cut this in vertical, how it will be looking like? I mean vertical in the sense like this, okay. So when how it will be looking like, I will be seeing like a rectangle when I cut it, right. So when I cut it, it will be looking like a rectangle. And what is this is called elevation, okay, elevation pattern. Now azimuth pattern, what is azimuth pattern? When you cut this horizontal, when I cut a cylinder horizontally, and if I see from the top, it will be looking like a circle only, right. So that's what this is called, azimuth elevation, azimuth pattern, okay, sorry, this is called azimuth pattern. Now these are the two ways how we study the radiation. Next is 3 dB bandwidth. What is the 3 dB bandwidth? Here a fundamental property of an antenna is its ability to focus power in a given direction, okay. Basically any antenna is designed to focus a wave in a particular direction. Thus an antenna with a broad main beam can transmit uh, can transmit or receive, basically, sorry, can transmit or receive power over a wide angular region, while an antenna having a narrow beam will transmit or receive power over a small rectangular region. What is here? We can see two terms. What is wide broad antenna, sorry, narrow main beam and broad main beam. What is a main beam? What is a main beam is when I try to transmit through an antenna. For example, this is an antenna, there will be one main lobe and there will be some few side lobes will be there, okay. This is called main lobe, okay. So broad main beam is when this main beam is broad, that means wide. How it will be when it is narrow like this? How it will? So when it is broad main beam, then what happens? The power overall power wide angular region can transmit, okay. So when the beam or the beam width is so wide, that means let us take an example like this. This is so wide, that means it can cover this much region, right? The signal can able to transmit along this much wide. But when it comes to narrow, it only focusing on this direct only small region. It can transmit in a particular focused direction only. The wave will be transmitted. The power of the signal will be transmitted. So one measure of this focusing effect is the 3 dB. 3 dB. So how to measure how much focus how much effective is this focus is with the help of 3 dB beam width at the antenna, defined as an angular beam width of a main beam uh, at which the power level of the has dropped 3 dB of its maximum value of its half. So basically maximum value 3 dB. When it's dropped to 3 dB, that means it's called half power point. So basically in this at the particular level, at a particular level, let us assume, for example, the maximum power that is 10 dB. At a particular level, we got a 7 dB. That means basically it is a 3 dB drop is there. So that particular level is the half power beam width. In this diagram, here in this line, at this line, the power is reduced by 3 dB. So that's why this point is called half power beam width. And also basically we can see how we got. So, or you can say another way also, you can say basically. So other way to understand from the diagram is, when you observe this side lobe, sorry, main lobe, when you draw a parallel lines like this, okay, and there are wait, I'll write in the same. Let us take this diagram only, you will understand. So basically I will take this diagram here. Okay, in this diagram you can see this is the main lobe, right? I will share it. So this is the main lobe. See this main lobe, how much it is like this. Okay, this is called half power beam width. Beam width is in terms of angle only, it will be in degrees. That's basically the angle made by these red lines. Okay, when it comes to this is first null beam width, okay, not full, first. So first null beam width is like for this minor lobes here, we need to add a line. Like for example, if I zoom that, a line passing like this, touching this next side lobe. So when for example this is the main lobe, what I draw in the red is this, touching the main lobe. This line touches the main lobe, like a what you call tangent line, like a tangent line. So basically the angle made by this yellow lines is called first null beam width, and the angle made by this red lines is called half power beam width. That's it. So that's what we'll see when it is a 3D power pattern. Now when it comes to 2D power pattern, it will be looking like this. In the center it will be a main lobe, the remaining basically except main lobe, the remaining all are called minor lobe generally. In this minor lobe there will be side lobe, back lobe, like that. So this is a side lobe, this is the back lobe. Okay, so beam width more direction, more antenna. So basically what we can say, basically when the beam width is less, then we can say it is more directional, because it can be focused in one particular direction, right? Here in this example, you understand? So in this example you can see it is not focusing in a particular, it is focusing in this direction, this, like this. When it comes to narrow beam, it is focusing on one direction. So that's what, more direction. Antenna has a constant pattern in the azimuthal plane are called omnidirectional antennas. Antenna having a constant pattern in the azimuthal plane. So azimuthal plane is what, when you cut that 3D pattern, in, but horizontally if you got a constant plane, so then we call it as omnidirectional antenna. These are uniform for applications such as broadcasting. These are the useful for applications such as broadcasting or for handheld wireless devices where it is desired to transmit or receive equally in all directions. Because in this what happens, the radiation pattern will be transmitted in all directions. And okay, so those there are few applications like wait. Okay, like some of the devices like handheld wireless devices, broadcasting, etc. The patterns that are relatively narrow main beam width in both planes are known as pencil beam width and are useful in applications such as radar and point-to-point radar links. So when the main lobe is so narrow and it will be looking and in both planes in the sense one is azimuthal and another is elevation, right? So azimuthal and elevation pattern. So in both planes, it's narrow. When you see if the in both planes, if the power pattern is narrow, radiation pattern is narrow, are called those signals are called pencil beam antennas and are useful in applications such as radar and point-to-point radar links. Okay. Now coming to the relation for directivity. What is directivity? Another measure of focusing ability of an antenna is the directivity. It is defined as the ratio of maximum radiation intensity in the main beam to the average radiation intensity over all space. So when it comes to directivity D, so D is defined as the maximum radiation intensity, what I told U, right? So that's a U max by U average. So maximum intensity by average intensity. So that's what we are writing, and for I have converted this U average into P radiated, like U average is equals to P radiated by 4 pi. From that I have wrote guys. So now directivity is a dimensionless quantity because both are power radiated and those will be for intense radiation intensity. That's why those two will be cancelled out. Next, an antenna that radiates equally in all directions is called as isotropic antenna, applying for the ideal radiation. Okay, an antenna with equal in all directions. Basically, if the antenna radiates a signal equally in all directions, then we call it as this isotropic antenna. Okay. And what happened to the denominator of the whole? So what happens here? We got D is equals to this, right? In this I am solving for this integer where we got this as 4 pi. So substitute there and we got okay, shows that the derivative of an isotropic element is D1, D is equal to 1, that is 0 dB. Okay. Since the minimum directivity of an antenna is unity, because we can get this ratio as 1 only, right? At max, that's what. Since the and not in the sense what he is saying is when U average is equal to U max is equal to U average of any antenna is unity. Since so that's why we call that one as minimum directivity of an antenna in is unity. Directivity is sometimes started as relative to directivity of an isotropic radiator. So he is telling that the antenna that we have calculated will be definitely told in the class. Okay. So what happens? Since the minimum directivity of any antenna is unity, directivity is sometimes started as relative to the directivity of an isotropic radiator and written as dBi. So this will decimals, written as decimals. So typical directivity of some common antennas. Okay, directivity of some common antennas are like examples 2.2 dB for a wire dipole, 7 dB for a microstrip patch antenna, like that. Now relation between directivity and 3 dB. So we can relate this 3 dB for but this formula is not for everything. So for only for particular type only. So one such approximation we are approximating to find D. Okay, for the pencil beam pattern. So for a pencil beam pattern, what is the directivity? D is approximated to 32400 by theta 1 theta 2. And also you have to remember that both directivity and the beam width concepts lead to find what is the antenna pattern. Okay, so basically the beam width and the directivity are both measurement of focusing ability of an antenna. So how beam width and directivity then anyways the formula is how directivity towards the so towards a particular direction. Now how to tell beam width? So basically beam width can be told by given, right? If the beam width is more, what happens? Basically I'll tell you an example to remember this, where let us take two cases. One is a thin person. So if a person is thin, what happens? He can travel through long distance. Okay, if a person is so fat, then he can't able to travel. So this is the distance travel, okay, by lean person, here by fat person. This is an example. The formula for directivity of a pencil beam with pattern is D is upon 32400 by theta 1 theta 2, where theta 1 theta 2 are beam widths in two orthogonal planes. Okay, so for now let's stop here. In the next lecture we'll see what is gain and radiation efficiency of an antenna. Thank you for watching. Like, share. If you need us, you can comment in the comment box.